Okay, our final circular motion video, part D, we're going to look at some banking angle example problems. So just some problems that look at what we've covered in the last video. So finally, I just want to go through an example calculation. This is a previous exam question of a typical banking angle question. So the exit of a freeway has been designed so that a car can travel safely around the curved section of the ramp when the road is wet. The banking angle theta enables a car to travel around the curved section of the ramp without relying on friction as shown in the diagram below. On the diagram below, draw and label vectors to show the normal force acting on the car. So the normal force comes out of the road at 90 degrees. So that is our normal force. Then it says, using the vector you have drawn in part A, explain how the banking angle enables the car to travel around the curved section of the ramp without relying on friction. So I'm going to add to my diagram here because this is actually going to help my explanation. That normal force has a vertical component and a horizontal component. So at the moment, I think you've already, without even writing anything, got 1 out of 3 for this question, because you've clearly shown that you realise there's a horizontal component to the normal force. So just to be safe, I'm going to repeat myself here. As seen above, there is a horizontal component of the normal force directed towards the center of the curve. So I think almost got a mark there for being clear that we understand it's directed towards the centre. This force can cause a centripetal acceleration. Oops, that was a bit messy. Oops. Can cause a centripetal acceleration. Let's just use undo. Can cause a centripetal acceleration causing the car to turn without the need for friction. So we don't need to rely on friction between the road and the tyres. So I would say there a mark for clearly demonstrating that you understand there's a horizontal component, realising it's directed towards the centre, and therefore it causes centripetal acceleration, which the car needs to turn. And the second one really is well, the next part is just a substitute into that calculation. It should be really straightforward. These are normally done pretty well in exams. So we know that the radius equals 150 metres. We know that the angle equals 11 degrees. And it's asking us the maximum speed. So we know the relationship says tan theta equals v squared on rg. Sorry, and we also know here that gravity is equal to 9.8 meters per second. So if we rearrange that formula, times both sides by rg, cancels that, cancels, and to get rid of the v squared, we need to take a square root, both sides. So we get v equals the square root of rg times tan theta, which is equal to the square root of 150 times 9.8 times tan of 11. Make sure your calculator is in degrees, not radians. And we get the velocity is 16.9 meters per second. So, just trying to think, 20 meters per second is about 72 kilometers an hour. So that's probably 60 something kilometers an hour that you could go around that corner and not rely on any friction at all. Okay, that's it for the circular motion notes. Time to get stuck into your workbooks and complete the circular motion questions now. And once again, if you're not sure about anything, if you have any problems, please sing out, ask questions. Thank you.